Hello community, so great that you are back. We have a new reinforcement learning idea and a brand new paper. I already showed you in my last week's video, September 18. We have here flow reinforcement learning matching the reward distribution for LLM reasoning. And if you just look here at the Kullback-Leibler divergence here for reward maximizing here for PPO and GRPO, you see we are really high. And if you look here for flow reinforcement learning, you see that our Kullback-Leibler divergence here, the difference between two probability distribution, is almost zero. And this is exactly what we want. So what beautiful thing is here right in front of us. Let's have a deep dive. Now, you know, whenever we fine-tune here our new reasoning model, our huge reasoning models, you have here the fine-tuning, you go with a PPO from 2017 or DPO or whatever you have, but you fight always against the mode collapse, where your model output becomes repetitive and lack a diversity, and it's just collapsing into one-dimensionality. Now, flow reinforcement learning is not just a clever hack, it is a complete new idea with an extensive mathematical body from the generative flow networks, GFlowNets, and the energy-based model, providing here really a solid mathematical justification why this system now is the new reinforcement learning paradigm in AI. Because you know what it does? It reframes the policy optimization by data. I know, it is fascinating. So we have to learn a little bit. I had to look at this paper here. This is from 2021. This is here from Benjo. It's here one of the first works about the flow network-based generative models for this idea. And he says, you know, I want to have a view of a generative process as a flow network, making it possible to handle here the tricky case where different trajectories can yield the same final state. And he did this here on the molecular graph complexity. Now, if you look at this, what's the most important idea in this paper? You say, hey, I do have a Markov decision process, and now I view this as a flow network. So this means I leverage here my directed acyclic graph structure of a Markov decision process and learn a flow, rather than estimate here my pseudo values as a sum of descendant rewards as elaborated below. So a flow network Markov decision process, and you immediately understand, if you have seen my video, that every AI model runs on uncertainty. And of course, at the core of every AI is a partially observable Markov decision process. Why this is here really shaking here up the base of any AI model that we have today. Now, in the study, they go here on the flow condition that require for any node, the incoming flow equals the outgoing flow and the total flow and everything that is great. But you know what's really important is here, they found here to compute here a loss function. And now you see the loss function at first here is a square, which makes it much easier. And we have the logs of our expression, and I will explain later why this is so beautiful. So we will use now this complex mathematical apparatus for reinforcement learning. And you said, okay, but we were talking about reinforcement learning. So how does it fit now if we have a reward distribution? How can we reduce our Kullback-Leibler divergence here from a horrible 8.6 to a beautiful 0.1? Well, that's it. So let's have a look. And I do not want to give you right in the front of the pure mathematical explanation, but I would like to explain it in simple terms. And I would like to find an example that makes it simple to understand, because a lot of my subscribers ask, can you explain it in simple terms? So I will try my best here. And I invested more time for the simple explanation than for the mathematical explanation. So I would say, let's start here. So I want to understand here this complexity from a flow perspective view. No? So I say I have a flow, whatever the flow is. So let's go with the flow that you can imagine, a flow of water. So we have rain, we have clouds, and it's raining over the mountains. Yes, I'm sitting here in Austria, beautiful heart of Europe, and this rain is here the source of the water, you know? So we have a flow pouring down. And then we have here a complexity. And now this complexity is a three-dimensional mountain terrain, as you can imagine, no? Rocky terrain all over. This is here our complexity representation in this Gedankenexperiment. And now the water is raining, flowing down here, this complex terrain on the Rocky Mountains into different valleys. And now in those valleys, now that is more or less our stable conditions, they have different fertility scalar indicators for the crops that grow in this valley. So you see, a simple idea. Now, the flow reinforcement learning is now a mechanism to steer here the right amount of water into each of the valleys in our mountain, given here the particular fertility scalar indicator of each and every particular value. So every value should have the right amount of water to make it prosper. The aim is now to have a perfect flow from the rain, raining down here on this rocky terrain, to provide now each path down the rocky terrain down to the valley. And this path is, of course, here the reasoning path, the chain of thought path, if you want, from the LLM that is generated, with enough water to irrigate now the soil in all the valleys perfectly for their specific scalar fertility coefficient, for their complexity. Now, let's have a comparison. Maybe you don't get it immediately. So what is the rain over the mountains? The rain over the mountains is simply the initial state of our complete system. It's your prompt. So this is the source of all potential solutions. No? So for a given mathematical problem, this is the problem statement itself. Find here a quantum field theoretical explanation of ABC. Great. Then the flow of water. The flow of water is in our statistical model, of course, the probability mass that we are dealing with. And the amount of water is the probability itself. Either you norm it to 1 or 100%, doesn't matter. Flow reinforcement learning decides how to distribute this particular probability of the probability mass or of the flow of the water down over the rocky terrain. And the rocky terrain is, of course, our gradient landscape. So the mountain terrain is the space of all possible token sequences. Let's change to this perspective. If we say the mountain terrain is the space of all, if you want, answers given over those token sequences or short token sequences or short sentence, whatever, a vast complex landscape of all possible chains of thought that lead to the solution of the problem. So some paths are easy and direct. This will be our deep channels. Other are convoluted and unlikely, so have a low probability, some rocky trickles only. But there's more. Now, of course, there's the path down to the valley. And this is now in the complexity a reasoning trajectory. Why? And if you want, this is our chain of thought. So this is like here a specific sequence of steps. This is the answer given by our LLM or our coding LLM. If you say, hey, I want a solution to this sequence of codes, or a mathematical LLM where you say, hey, solve this particular equation, it's the answer. Path down to a valley. But the valley itself now, as I told you, are the final solution, or if you want to see this from a state representation, the terminal states here of our system, this are the end of the reasoning path. We have an answer, yeah? The final answer generated by a vision language model or an LLM. Now, the fertility of the value is, of course, remember, we are working here in the reinforcement learning representation, the reward function. And let's go here with a scalar reward that has here, I called it here the fertility of the land. A high fertility value represents, of course, a correct, elegant, or high quality solution, so a high reward reply. And if you have here a barren, rocky valley, this is more or less an incorrect solution. So I'm working with this very simple analogon, you see? Yes, of course, looking out of the window, I almost see this. So you understand why. So the current way to do this, the current algorithms like PPO and GRPO are pure reward maximizers. So they behave like an aggressive civil engineer that comes to the mountain, one goal, maximize here the crop yield in the single most fertile valley. So the engineer says, hey, I see 7 valleys down here, looking down from the mountain, but only 1 green valley. And now I focus all the water, the downstream here to this single valley. This is a reward maximizer, no? But we don't want this. We want to have here new solution. We don't want that every system just collapses here to one particular solution. We don't want a mode collapse happening for our system, but because this is what's happening. Now, in our GFlowNet result, we have one champion valley here. This is perfectly irrigated and incredible productive here. And this is the go-to solution that the AI has for a particular problem, coding, explanation, whatever you have. And all the other values, all the other possible solution paths, even those that are maybe a 90% correct, yeah, but have maybe a path that would be essential for the next problem, for a higher complexity problem, we would have to explore this valley with only 90% fertility. It is now dried out, becomes arid deserts. So the reasoning ecosystem collapses now into a single mode, and we only have a water pipeline down into one valley, into one, if you want, solution for one particular problem. But imagine we modify now the problem. Then this known path will not provide any solution anymore, and this is what we say is a mode collapse of our reasoning system. Now, what is the solution? The solution is a flow reinforcement learning system, and this is now a distribution matcher. It is now not looking for the perfect singular answer, but it is looking at a complete variety of answers. So let's say it acts like a wise ecologist trying to create here a healthy, diverse, and resilient watershed. The goal is now to ensure the amount of water reaching now each and every valley is perfectly proportional to its natural fertility. So to a solution we found there down in the valley. So we follow the reasoning path, we learn the reasoning path, we explore the reasoning path, even if they're not 100% correct, but also maybe 90% correct, because the next task to this AI might be a higher complexity level, and then it has to find new pathways forward. So you might ask, how does flow reinforcement learning achieve this without building now dams and just focusing on channeling everything down to one valley? Well, the idea is, and this is a little bit, that's a little bit a challenge now, it reshapes the three-dimensional mountain terrain itself, because if we look then at the mathematical representation, it changes here our policy pi theta. Theta are the parameters and the weights and everything. So this is here, if you want, where the magic of the flow balance objective function comes in. This is now where here this new mathematical the new mathematical apparatus here of the flow distribution come into reinforcement learning. Now let's look at the core objective again through the lens here of this water flow. Now we can rewrite now some of the equation here into this very simple flow equation, or to make it here even simpler here in my example now with the rain. So we have a term that is more or less the total rain. Now it's the water pouring down from the sky. This is here, if we have a flow-based analysis, this is the total rain, the input. Then we have a lot of pathways with a particular flowliness. How fast the water goes down this particular reasoning path down to the valley, down to the solution. And of course, this has to be proportional somehow then, at the end of the flow, the target water that arrives in all the different valleys. So you see, simple idea. Yeah, if you're not familiar here with this notation, a lot of people always ask me, what are you talking about? What is a pi theta? It's a probability of the model generated. If you have here a specific prompt X and you want to generate a specific answer Y, so you see this is here simply the strategy or the policy pi theta, where theta are the free trainable parameters of the system. Now, look at this from a different perspective. Here, the first term here, it's of course log for simply we have just to sum and not multiplication, the total rain. It's a model estimate of the total amount of rainfall for the entire mountain range, for the specific prompt, for the specific task. And of course now the problem is how to determine this parameter. More about this in a minute. Then I already told you here we have the strategy or the policy pi theta. It represents how easy it is for the water to flow down here, a specific solution path Y, given the complexity, the task complexity X. So a high probability path is like a deep, smooth riverbed, and a low probability is just a tiny trickle of water down to the valley. And here, of course, our R, guessed it, this is the reward function, the target amount of water that should end up in the valley at the end of each path, Y, based on its specific fertility, scalar fertility efficiency. And you see, it is a very simple equation, no? Yeah, again, this here, why we have here the log, again, I was asked here, hey, we can transfer this here instead of a chain of multiplication into a much more stable sum, and here you have the sum. So this is just to have a simpler mathematical calculation. But how this complete balance act works now here if we have multiple values and multiple rivers downstream, multiple augmentation paths, multiple complexities that we need to explore. Now, we have more or less two options. The valley is under-irrigated here by this stream of the rain. So what is happening? We have an equation that is imbalanced. We have a very high loss function. To fix this, the optimizer will erode now the path leading to this valley, carving here a deeper channel by increasing here the policy probability pi theta. More water now flows down there naturally because the fertility of this valley is high. It just needs more water. It just needs a better reasoning path to this particular solution. Or you have the exact opposite, no? A barren valley is over-irrigated. So again, the equation is unbalanced. The loss is also really high. So the optimizer will now try to, let's say, reduce here the flow by depositing here some sediments into that particular downstream path, making it harder for the water to flow. And of course, yeah, this is our regularization terms in mathematical speech, but I want to give you a simple example by decreasing here the policy probability pi theta. Great. So you see, okay, it's just a control loop. No? Now, by applying now this balancing, if you want, pressure all over again, over every path, everything that it samples, it doesn't just force here on a single unique solution, but it adjusts here, think about the different valleys here, the entire landscape of the probabilities until a beautiful equilibrium is reached. The flow of all the probability mass naturally distributes itself across all reasoning paths into all the values that are fertile in a perfect proportion to the resulting rewards. This is the fertility scalar. So you see, I try to explain a mathematical complexity in a very simple image. Now, you know, of course, so you understand this pi is here the policy or the strategy of our agent deciding now what is the next action to take. This here is here the target water that is in the valley. So more or less now we just have to focus here on the first term here on what is Z. What is this Z? And let's have a look at it. What is in my example, what it is in a mathematical construct. Now, we already identified Z psi here as the total amount of rainfall. But there is, of course, a twist. No? Nobody knows what the total amount of rainfall will be. And no chance at all if you know this in advance. So, if you want to see now the mountain range in its totality, it is, of course, the problem space that we have to look at and we have to explore. You remember explorability versus exploitability here in reinforcement learning? And now this problem space is vast and unknown and no idea. So you just can put a giant measuring cup over it and just collect here all the rain or measure this somehow. No? So you hire now, and this is the solution here, a learnable weather forecaster. And this weather forecaster is nothing else here than our neural network Z. Set of psi here, let's start the flow. So at the beginning, the forecaster has absolutely no idea. We have to learn this system. We have to train this system from scratch. So no idea how much reward potential a problem holds. So for a new mountain range, a new prompt given by the human, it might make now just a guess. It just starts here. Now it said, hey, I predict a light drizzle today. So a small value for Z. And then the system lets some water flow naturally down a few paths. So the given policy pi theta generates here a few reasoning trajectories Y. And these are like exploratory probes. Now, and these probes flow into different valleys. And let's say you can measure them very simple here. What is the effect of the water in the valleys? You have a certain fertility. And this, of course, is our reward function. So the results are now observed. Remember, Markov decision process, partially observable Markov decision process. So let's, in our example, those are observed, the probes are sent back to the weather forecaster. So if we have an underestimation, the forecaster predicted a light drizzle, but the probes discover several incredible fertile valleys, no? So there's a high reward coming back, says, yeah, if you give me more water into my valley, I will have a crop production 100%. So there is now a mismatch of what it could be. So the system knows that the forecast was wrong. So there's far more fertility potential in the valleys than it was expected. So the loss function now, the learning of the system is now in a way that the loss function penalizes now the forecaster for its slow prediction, forcing it to increase the estimate of Z. And guess what? If we have exactly the opposite, an overestimation, the system also penalizes here the forecaster for being too optimistic and forcing it to decrease the estimate of Z. So you see, we will have a loop that comes to an equilibrium. So the Z network isn't just measuring the total rainfall, it is learning to predict, like any AI system, the total integrated fatality of the entire landscape, given we have a particular flow from the rain over the complex mountain terrain into the multitude of valleys. So it learns this here by constantly comparing its global forecast against the local evidence gathered here by the individual water flows and the result of the water flows that make here crop prosper and blah. Beautiful. So let's come back and have a different perspective. Z is now the self-correcting estimate of the total reward budget, of course, which allows here the system now to make sense of the individual flows. So the system is learning, a self-correcting, self-learning system. And a river flow is only meaningful when compared to the total amount of rain that feeds it. So let's have a look now, since we have now this understanding here of a flow in and a flow out and a flow balance equation. What does it mean in scientific terms? It is nothing else than a partition function, a learnable partition function for the system. Now is the time that I tell you, if you really want to have a deep dive, I would recommend this paper. This is my weekend paper. You have here 75 pages here. This is already from June 2023. Real interesting, the GFlowNet foundations. Have a look at this. This is a detailed mathematical, gives you everything you need to know. But we just want to focus here on the main idea, the main understanding before we have a mathematical deep dive. So what is the goal? The goal is to create a target probability distribution where the probability of a solution y is proportional to its exponentiated reward. So our reward function, let's just say reward function, forget the beta, forget the exponential, our reward. And to make this a valid probability distribution, to make it to sum over 1 over all probability distribution, you notice we must divide it now, of course, by a normalization constant. And guess what? This normalization constant is our partition function Z. Now, isn't this beautiful? This is it. Yeah, absolutely. So, what is Z? How can we calculate Z? It is this idea is simple, no? You go through every possible single reasoning path y in the universe of all the solution of the set of y, calculate its reward function here with a hyperparameter and exponentiated and everything, and then you add them all up. Now there's a problem. No? If you have all the possible reasoning path, this is unlimited almost. No? It's astronomically. No? So there's no way you can compute this. No? A fundamental barrier. And this was a problem. And now the idea that flow reinforcement learning is, and it kind of borrowed this from the mathematical framework of GFlowNets, is to say, hey, if we can't compute it, let's learn to approximate it. So they create now a separate, simpler neural network Z, psi, with your parameters. And the sole job of this neural network is now to output a single scalar number that is our best guess at the time for the value of the log of Z. You see, it's approximation wherever you look. Now, there is now the next beautiful idea is you say, how do we build this loss function? And you want to say, hey, let's train this simultaneously. No? So we train here the policy network, our strategy of our AI system, and we integrate this with the training here of our set neural network. And we build this using here the same loss function. And here you have this loss function. And it's a trajectory balance loss, as you see, which is the core objective function that FlowRL seeks here to minimize. Look how beautiful it is here, our expectation. Now, of course, this loss, and you see here our Z function and our strategy and our reward function here, this loss creates here a beautiful self-consistent loop. So for every sample Y, the loss implicitly tells Z what its value should have been to make the equation balance out. It's a flow equation, no? Given the current policy's probability pi theta and the observed reward R. So average now over many loops and samples, our Z is now pushed to converge to a value that is consistent with the reward distribution being explored by the policy, by the strategy itself. This is the beauty. So again, have a look at this loss function. has an elegance to it. No? The loss function penalizes here the model whenever the probability it assigns to a reasoning path is not proportional to the reward that the path achieves, thereby teaching it to match the entire reward distribution. Remember the very beginning I showed you here that the Kullback-Leibler divergence here from FlowRL is almost 0.11. Extreme small. This is the reason. This is the main understanding what's happening here. If you want to see it here in your initial flow, your path probability and your terminal reward. This is here what the system learns simultaneously. So, main insight. Z is here a tractable, learnable stand-in for an unsolvable global normalization, computational unsolvable global normalization constant. And this, if you want, trick allows here flow reinforcement learning to frame the reinforcement learning exercise as a distribution matching problem without ever needing to compute here this impossible sum, turning here a theoretical elegant but impractical idea into a really working algorithm that we can use now for reinforcement learning optimization. So this Z is the key technique. And if you read the paper, yes, of course, it's in a relation to the energy-based Toggle distribution. Have a look at it. It's beautiful. So therefore, if you just want to remember one sentence, this is it. This new methodology of flow reinforcement learning cleverly uses now here from the separate mathematical body of GFlowNet trajectory balance objectives as a stable and practical surrogate for what was currently impossible to calculate for the intractable Kullback-Leibler divergence minimization objective. So we found a way to come close to this. So you want the distribution of your model output, your pi theta, to be identical to the true reward distribution pi gilde. And of course, you know how the mathematical tool to measure the difference is called the Kullback-Leibler divergence here. And the perfect objective is to minimize this value to 0. And with FlowRL, as I showed you at the very beginning, we're real close, 0.11. Now, yeah, as I showed you, the Kullback-Leibler divergence, if you really want to do this, is almost computational impossible to do. So therefore, we have this beautiful, as I showed you, trajectory balance loss here with our terms that we went through. And this is now the objective function that the FlowRL minimizes here as a mathematical thing. Now, look at this. You will notice there is now a beautiful simplification that helps us immensely in the computation. This formula doesn't require summing over all possible y's, all possible solution paths at the same time. You do have a stable squared loss form rather than the complexity of a Kullback-Leibler optimization formula. And this is one of the most important formulas you will see in the complete preprint here. Have a look at proposition 1. This explains why you're allowed to do this. You have here your minimization of the Kullback-Leibler, and then you say, why suddenly I can go to a trajectory balance function? Now, they prove here in a mathematical formula that if you consistently minimize the local, easy to calculate trajectory balance error from random samples y, this here, the gradient, so this means the update direction for your model on a complex manifold, are the same as the gradients you would have gotten if you would have magically, with unlimited computer power, calculated here the global, impossible to calculate a Kullback-Leibler divergence. They say this is here, for the gradients, they're the same. This is not easy to understand. It is not easy to understand this on a mathematical level, but they provide some beautiful guidance, and this is what I will enjoy this weekend. Okay, so here we are now. Flow reinforcement learning replaces here an impossible global comparison with an easy and efficient local balancing act that achieves here the same net result with our flow. Now, of course, you might say, okay, so what we have now for reinforcement learning from human feedback and PPO and everything, and GRPO and DPO, now we have flow reinforcement learning. When to use what? What is better? What happens? Of course, you find here in the paper, yeah, this here, the last one is here the best, outperforms 5 to 10%, everything else, but it is not that simple. Just let's have a look at this. So I would formulate it in a different way. The GRPO aims to maximize here the scalar reward, and its goal is to find the policy it produces here, the pi theta, the highest possible score. It's a peak climber. It looks just for the highest mountain peaks. No, this is it. DPO is different. It maximizes here the log likelihood of the human preferences. No, it is, if you want, a preference maximizer. And now, what is flow reinforcement learning? It aims to match your target probability distribution derived from the rewards. So its goal is for its output to reflect the entire landscape of all the values of good solution of all the good fertility scalars in proportion to their quality. So if you want, it is a complete ecosystem manager. So you have a peak optimizer, a preference optimizer, and then an ecosystem optimizer. And given that your task will increase in time and you will have higher complexities to solve, an ecosystem manager might be the right way forward. So therefore, I would now say, if your task requires creativity, kind of a robustness from the mathematical and computational side, and finding a multiple valid solution for mathematics, strategic planning, or any scientific discovery where there's not only one path forward, there are multiple solution paths, and you just have to find the right combinatorial multitude of those sub-paths, then flow reinforcement learning represents here, I think, a better paradigm to find a solution. Because, why? It addresses here the fundamental weakness we have in the other systems here, mode collapse. And it really is here mode collapse, something that we have here in GRPO and everything that plagues here the maximization-based methods on those complex domains, especially if you go to mathematics or strategic planning or planning tool use and so on. So therefore, I think this study here by Shanghai Jiaotong University, Shanghai AI Laboratory, Microsoft Research, Tsinghua University, Peking University, Renmin University of China, Stanford University, and Toyota Technological Institute at Chicago. This is a beautiful paper. You have to have a look at this paper. I think it's really a significant better solution for the next frontier of AI systems, especially for complex causal reasoning. I hope you enjoyed it. If you subscribe, I see you in my next video.